All right, so in chapter 2, the two loose ends we didn't cover was ionization energy and electron affinity. And that is going to, I don't know if you'll appreciate it, but it's going to relate to this chart, which we get to in chapter 3, electronegativity. So let's just, I'm not going to dwell on this. In your homework assignments and quizzes, they're going to have some questions where they say, okay, here's 3 elements, put them in the order of their increasing ionization energy. Or here's 3 elements, put them in the order of their increasing electron affinity. So how would we predict that? First of all, let's figure out what that is. Ionization energy is the energy required to remove an electron from an atom. Ionization energy. So if we wrote a little bit of an equation, it would be this energy plus the sodium atom yields a sodium ion plus an electron. We've removed that, gotten that electron off of there. This is an experimentally determined value. Okay, now try to start piecing some things together that I've told you. What have I told you metals are? What do metals do? They tend to form positive ions. And look, okay, they tend to lose electrons and form positive ions. I'll put that in that order, because that's what causes them to become a positive ion. They lost an electron. So just knowing that metals have this tendency would suggest that it's not going to take a lot of energy to encourage a metal to do this. Nonmetals, on the other hand, are the opposite. They tend to gain electrons and form negative ions. So just from knowing that, we could conclude that metals have low ionization energies. Nonmetals have high. It takes a lot of energy to get an electron off of a fluoride ion. It doesn't want to give up an electron. It wants another one. It has 7 in the outermost energy level. All right, so there's sodium, there's chlorine on the other end of this thing. So sodium is a metal, low ionization energy. Chlorine, fluorine, nonmetals, high ionization energies. All right, let's see if that's what bears out. My light switch person isn't here this morning. I'll take attendance here in a minute, or before we leave today, probably while I have you working on some of these worksheets. All right, let's see. There's sodium. Now what we got here is ionization energy there, and we're increasing atomic numbers. So there's 11, 12, 13, 14, 15, 16, 17. There's chlorine right there. What's happening? Ionization energy is increasing as you go from a metal across the periodic table to the nonmetal, chlorine. You with me? That's about what I want you to know about ionization energy. We're talking about the amount of energy to get an electron off an atom. It's relatively easy with francium, with sodium, potassium, rubidium, cesium. I mentioned francium. Francium wants to give up that electron so badly that you can't buy a bottle of francium. You can't get it in its metallic form. It's an elemental state. Just can't get it. You put it in a glass bottle, it reacts with the glass. Put it in a plastic bottle, it reacts with the plastic. It is extremely reactive. Can't hardly, because once it gives up that electron. So it doesn't take much energy to get it to do that. And let's just show it one more time here. There's lithium, beryllium, boron, carbon, oxygen, nitrogen, fluorine. See that trend? From a metal to the non-metal, increasing ionization energy, increasing ionization energy. So if I gave you these elements, let me just give you these right now. I'm going to give you fluorine and oxygen and nitrogen. Now put those in order of increasing ionization energy. Increasing. So what's the one with the lowest ionization energy? Nitrogen. And what's the next one? Oxygen. And what's the next one? Fluorine. Okay? So nitrogen is less than oxygen, is less than fluorine in terms of ionization energy. I'm not going to dwell on these. I just want you to just know what we're talking about. Okay, now, the next one, electron affinity. Okay, affinity. Attraction for an electron. This is the amount of energy that is released when you add an electron to an atom. So here we've got bromine. Always keep in mind when I mention an element, you should immediately be going to where is that in the periodic table? Here's bromine. Plus an electron forms an ion, bromide. Plus it releases energy. This is an exothermic process. You'll learn those terms in chapter 7. But this is a process that releases energy when you do it, electron affinity. Now tell me, I just told you that's a non-metal. Is this something bromine has a tendency to do, to lose an electron? Yes. Non-metals tend to, I'm sorry. You answered that correctly. Does bromine have a tendency of gaining an electron? Yes. Okay, I asked the question wrong, and so you answered it correctly, but the question was placed wrong. We've got bromine here gaining an electron. Bromine is a non-metal. This is something it tends to do, right? Gain an electron, form a negative ion. So in this case, you're going to get a lot of energy released when bromine, it's happy, okay? Affinity. This is the way it's happy with that electron. And it shows it by releasing a lot of energy. All right? So fluorine would be the same thing. It would have a high electron affinity, a lot of energy released when you do give it that electron. Whereas sodium, look at what that equation would look like with sodium. With sodium, let me write it on here. With sodium, we would have this equation. Sodium atom plus an electron yields a sodium. Now, what charge is it going to have? Well, that's the charge sodium normally has because it normally loses an electron. But it's gaining one here. So it would be negative. You're saying, I know you got a question on, well, can it do this? Well, it doesn't like to do this. So it gives off very low electron affinity, sodium. It's hard to get sodium to form a negative ion. Doesn't like to do that. So let's see what the trend is. Here is electron affinity. Atomic number, there's sodium, there's magnesium, sodium, magnesium, phosphorus, there's chlorine. Chlorine, to go to chloride, very high electron affinity, releases a lot of energy. Sodium and magnesium, very low electron affinities, almost zero. Magnesium's below zero. Here is lithium, beryllium, boron, that bounces around. You can see it's not just a straight line. That's why we call them a trend. This is a trend. But electron affinity increases as you go across the table. All right, the beauty about this is both of these things go in the same direction. Ionization energy increases as you go across the table, and electron affinity increases as you go across the table. They both have the same trend. So if we were saying here electron affinity, put them in the order of increasing electron affinity, it'd be the same order again, wouldn't it? Okay, that's good enough. These are experimental values. We're looking at the energy associated with these processes. And here is, this is just kind of, you can see here, ionization energy increases as you go across the table. Electron affinity increases as you go across the table. It increases as you go up, increases as you go up a column. This is summarizing these three major trends that I introduced you to: atomic size, ionization energy, electron affinity. And that brings us to back to chapter 3 that we started on Tuesday. And I said start getting familiar with this. These are electron dot diagrams. These are the valence electrons. And then there was a slide here, probably about here. Okay, we'll get to it. There's a lot of slides here. Yeah, this slide here that said, okay, if you go from those Lewis dot structures, you can start predicting, for example, sodium has that a Lewis dot structure. There's one valence electron. Everything in this column does. One valence electron. It loses that electron, forms a positive ion. Loses that one electron, positive ion. Francium would form a plus one ion. This is where this is coming from. It's losing its valence electron. The alkaline earth metals lose two valence electrons and become plus two ions. Aluminum. There's its Lewis dot structure. It loses those three valence electrons, forms a plus three ion. And then you get into here where fluorine has 7 valence electrons. It gains an electron. These form negative one ions. All right, so now let's kind of a little bit more methodically approach chemical bonding and chemical bonding is what's going to give rise now to compounds. We've been talking about individual elements, atoms, ions. We're going to now talk about how they are combining to form compounds. Chemical compound, 2 or more different elements joined together to form a new compound. There is a chemical bond between the elements in the compound. We're going to divide the chemical bonds into 2 distinct categories: ionic and covalent bonds. We talked about ions. What are ions? They're charged particles. So ionic bonds form between compounds where the opposite charges of the ions are attracted to each other. Okay? So that's normally, let's just use M for metal. A metal tends to form an M plus ion or a positive ion, it loses electrons. A non-M, an electron plus a non-metal forms a negative ion. So ionic compounds typically are a metal reacts with a non-metal. This is the basic formula for an ionic compound. This is thousands and thousands of compounds. This is where a metal reacts with a non-metal. You can take every one of these metals and react it with oxygen. Those are oxides of these metals. And you're taking a metal and reacting it with a non-metal. This is what most of the, well, many of the ores in the Earth's crust are that. Oxides of metals. Iron oxide, that's where we get iron from. Copper oxide, that's where we get copper from. Aluminum oxide, that's where we get aluminum from. All right, you take those metals and react them with oxygen. The atmosphere, the Earth's atmosphere, has got oxygen in it. And so these metals sit around and they corrode. They react with oxygen and they form oxides. You know, you take a car that's 40 years old and it's going back into the Earth's crust at a slow pace, right? It's turning back into rust. It's rusting. It's disappearing. That's what happens to iron when it's exposed to air. It eventually becomes rust. So these are ionic compounds. And all right, so the operative word here is you have the transfer of electrons from one atom to another. That's an ionic bond. I'll show you an example of that in a second. Covalent bonds generally are a nonmetal plus a nonmetal. Form covalent bonds, and the operative word here is the sharing of electrons. Sharing. Well, let's take something you would be very familiar with. Let's take carbon and oxygen. Carbon is a nonmetal. It's in the nonmetal category, and so is oxygen. And what do you get? You get carbon dioxide. Carbon dioxide is a covalently bound compound. The carbon and the oxygen are not ions, they are sharing electrons. Carbon monoxide, nitrogen dioxide, sulfur trioxide. They're all covalent. There's sulfur. So when you see two elements in the periodic table that are real close to each other, particularly when they are nonmetals, probably covalently bonded. All right? So sulfur trioxide, there's sulfur dioxide. These are all covalently bonded. We got a nonmetal with a nonmetal. What happened? I went back. All right, so how does that happen? So let's look at the ionic bond. We've got our sodium. There it is, the Lewis structure. There's its valence electron. It has a tendency to lose an electron and form a sodium ion. I say a tendency. If I had a chunk of sodium sitting here, and I'd say, well, it's not doing anything. No, it's not doing anything because it's not. It will only do this in a chemical reaction. But if you take sodium and you bring it into contact with chlorine, all of a sudden there is somewhere for that electron to go. And that's what happens. This thing transfers that electron to this atom to form that ion. You follow me? So simultaneously, right before your eyes, as a matter of fact, if you did this, it would happen so fast, probably break something. This would be an explosive reaction. It would give off heat and energy. right before your eyes, this is forming a positive ion because it's losing an electron. That is the electron it's losing. Chlorine is picking it up and forming a chloride ion. That is a chemical reaction. And the final product is a sodium ion bound to a chloride ion. There's no sharing of the electrons between them, really. It is the attraction of oppositely charged particles, ions. That's what holds the salt in your salt shaker together. Sodium ions attracted to chloride ions. Atoms with low ionization energies, sodium, and low electron affinities, sodium, form positive ions. Atoms with high ionization energies, high electron affinities, form negative ions, and so they react with each other very readily and form ionic compounds. This is what, so now piecing some of the things together. Here's your sodium ion, or sodium atom, big. It loses an electron, becomes a sodium ion. Remember, the cation is always smaller than the atom it came from. Here's your chlorine atom. It gains an electron and becomes a chloride ion. The anion is always bigger than the atom it was made from. It's gaining an electron. This is losing an electron, so that makes sense. Losing an electron gets smaller, gains an electron, gets bigger. And here it is. Here's our sodium ions right there. Sodium positive ion right there. I don't have the right color for that. And there's the chloride ion all around it. And there's another one behind it, and there'd be another one over here. If we didn't cut this off here, there'd be another one right here. There is a 1-to-1 ratio, 1-to-1 ratio of sodium to chlorine. But what happens if you start dropping these into a crystal, it starts crystallizing in there. The sodium finds a position that is near all negative ions. The negative finds a position that is surrounded by all positive ions. That's what's attracting them. If you had a big chunk of salt and you took a hammer and broke it, it would break along the line that it would break in such a way that you would have the same number of positive ions and negative ions in every piece of salt that you ended up with. As it broke apart, these ions would, the sodiums would be stuck to the chlorides would be stuck to the sodiums, and it would break in such a way that you'd have a 1-to-1 ratio. And so we say that the formula for sodium chloride is NaCl. There's a 1-to-1 ratio of sodium to chloride ions. All right, we'll get more complicated here in a minute, but this is simple because we got sodium losing 1 electron, chlorine gaining 1 electron, and so we get this sodium chloride 1-to-1 ratio. Now let's just contrast that with covalent bonding. All right, if we take, hydrogen exists as a diatomic molecule, H2. It looks like this. It wants to look like this. Helium is its closest noble gas. Hydrogen is so tiny it's never going to get an octet of electrons. Neither is helium. Helium only has 2 protons in there. But notice that 2 electrons fills its first energy level. It has a full energy level, like neon does. So even though it's not an octet, it is a very stable, inert, noble gas. So hydrogen wants to be like that. So how can it do that? Well, the only way it can do that is if it shares its electron with one more hydrogen atom, not 2 or 3 or 4, just one. Because one will get it right there. Let's just take a look at that a little bit bigger. So if I cover this, it looks like helium. It's sharing, this atom is got some, right to this electron. It's sharing its electron with this one, so this one's sharing its electron with this one. So in a sense, this feels like it has 2 electrons around it. This feels like it has 2 electrons around it, even though there's only 2 electrons. Follow me? They're getting to this place by the sharing of electrons between them. And so hence, hydrogen is diatomic. You buy a cylinder of hydrogen, this is what's floating around in it, are H2 molecules, not hydrogen atoms. You buy a cylinder of helium, or you go to HEB and you say, I want to get my sister a balloon. It says, congratulations. Well, they're going to fill it with helium. What's going to be in that balloon? Helium atoms, not molecules. Individual helium atoms. Why? Because the helium, it doesn't need to share its electrons with any other atom. It's got a good, stable electronic configuration, a filled first energy level, doesn't share its electrons with another helium atom. So they float around inside that balloon as individual atoms. But hydrogen doesn't do that. This is the way you find hydrogen. And actually, it's the way you find oxygen, it's the way you find nitrogen, and it's the way you find the halogens. All right? This is worth remembering. These 7 elements, 1, 2, 3, 4, 5, 6, 7 elements are diatomic. They are the best examples of covalent bonding. Why do they share the electron? They have the same attraction for electrons. They're identical atoms in the molecule. Both atoms in the molecule here are identical, so they don't transfer an electron from one atom to the other. They share their electrons in a pure covalent bond. All right. So we've got these 2 kinds of bonding: ionic, transfer of electrons forms ions, the opposite charges are attracted; covalent, nonmetal to a nonmetal, or the 2 of the same atom, they are sharing their electrons. Sharing. This is just kind of showing. I mean, if we heated up hydrogen really hot, 2,000 degrees centigrade, you could bust it apart, be into individual atoms. And then if you cool it on down, you'd see the atoms getting closer and closer to one another and forming a hydrogen molecule. So what we have here is the electron clouds around an individual hydrogen atoms, and now you're forming a new molecular cloud, molecular orbitals that those electrons are in. Don't worry too much about that slide. It's just giving you an example. But here are these diatomic atoms. So here's fluorine. We just saw hydrogen. Here's fluorine. Fluorine atom, 7 electrons in each. And so what do you get? You get this I'll just put it here so you can see. We had 7 electrons here plus 7 electrons here, 14 electrons. 2, 4, 6, 8, 10, 12, 14 electrons. And what you will see me doing from now on is writing this. I'm going to take these two right here that are being shared, and I'm going to convert them into a covalent bond. I'm going to draw a straight line. That line is 2 electrons. And then really, to represent this properly, I'll put the non-bonded pairs of electrons still around the 2 fluorine atoms. And I can still count it, 2, 4, 6, 8, 10, 12, 14. Whenever I see a line, I know that that's representing 2 shared electrons. Right? And I just want to make it very clear. I've already said it, but just very clear. I don't have any more electrons here than what those 2 atoms had to begin with. I didn't just out in midair somewhere say, oh, I need another electron. You don't have that. When I say atoms are losing electrons, it's not like we don't know where that electron went. The sodium atom loses its electron to chlorine. We know exactly where it's going. Won't go anywhere unless there's a chemical reaction. So this is how a cylinder of fluorine, now these are all very toxic. Fluorine, chlorine, bromine, iodine. They're oxidizing agents. They're very reactive. It's not like oxygen and nitrogen, which we are breathing all the time. You wouldn't want to be around a cloud of fluorine or chlorine or bromine. Okay, so this is covalent. All right, now let's look at when we get dissimilar atoms coming together. Let's look at the bottom one first. This is one that you're very familiar with this, but let's look at this one first. Here is your Lewis dot structure for carbon, 4 valence electrons. There it is for hydrogen. So what does carbon want? Carbon wants an octet, right? So it only has 4 electrons. It wants 4 more. So how does it get that? It shares an electron with 4 different hydrogen atoms. And you get to this, and you would see me more often writing it like this. I would convert each one of those pairs of dots into a straight line, and there's 2, 4, 6, 8 electrons right there. 2, 4, 6, 8 electrons right there. There's no more dots around carbon. It doesn't have any lone pairs of electrons. It has taken each one of its electrons and shared it with a hydrogen atom, and you get this molecular formula for it, CH4. 1 carbon, 4 hydrogens. And this is methane. This is, or natural gas. This is the gas that is fueling your stove, your furnace. This is methane. CPS Energy is delivering that gas to our homes. And this is covalent bonding. Okay, now water segues us on into kind of the territory that is between covalent and ionic. You're gonna hear me start talking about polar covalent bonds, and water is that. But so let me just draw my water this way. There's my not my water, but my oxygen has group number 6. Okay, remember how you get here. Group number tells you the number of valence electrons. So I'm going to write an O with 6 dots around it. I'm going to pair up 2 of them. And so then if I bring on a hydrogen right there and share an electron and I bring on another hydrogen right there and share another electron, I don't bring on a third hydrogen. Why? Because oxygen now has 8 electrons. It's got an octet. It has achieved what it wants to, an electronic configuration like neon. And so you could draw it like this, which is normally the way I draw it. Right now I'm going to go one step further and include those non-bonding electrons so that you can see what we have here is 2, 4, 6, 8 electrons around there. We got 6 of them from oxygen and 2 of them from the hydrogens. So we have only the electrons that came with those 3 atoms, the valence electrons. All right. Now let's dig into this covalent bond a little bit more. Ionic transfer, covalent sharing, polar covalent, unequal sharing. That's what happens between the oxygen and the hydrogen. And to understand that, why don't they share them equally? We need to understand this. Electronegativity. This, unlike the ionization energy and electron affinity, which you can go in the laboratory and you can measure those energies and get numbers, this is a scale. This is a relative scale put together based on everything we know about these elements. Some of the key things we do know are ionization energies, electron affinities. We look at the nature of the compounds they produce. And someone years ago developed this scale. And it goes from 0.7 up to 4.0. Here's your smallest number right there, francium. Your largest number is fluorine, number 4. Oxygen and chlorine are close, 3.5. So these 3 elements right here in that corner of the periodic table have the highest electronegativities. Notice that this is not a periodic table. It's laid out like a periodic table, but the only numbers on here are electronegativities. And notice that we have left the noble gases off. This is a table that helps us predict the kind of bonding that any 2 of these elements will make when they react with one another. So what is electronegativity? The ability of an atom to attract electrons in a chemical bond. And so we're saying francium has a very low attraction for electrons. I've already told you that. It's a metal. It's not interested in electrons. It's interested in getting rid of one. You got me? So it has a low electronegativity. Fluorine has 7 valence electrons and is very interested, has a very strong pull for another electron, strongest of any element in the periodic table. All right, so electronegativity increases as you go across the periodic table. It increases as you go up the periodic table. So really it's increasing in this diagonal direction right here. Low in this corner, going up. All right, here's how we're going to use that. Now remember, let's look at this number right here. Where am I getting that number? If I take francium and I react it with fluorine, fluorine has an electronegativity of 4. Francium has an electronegativity of 0.7. And what I'm going to do here is the difference. Delta E is going to be the difference in electronegativity between the two elements. Difference. So I subtract the one from the other, and I get a 3.3 difference. Since I have taken the element that has the lowest electronegativity and I'm comparing it with the element that has the highest, that's the biggest difference you can get in electronegativities. This is the most ionic compound. If you said, well, are there natures? Well, francium fluoride is about as ionic as you can get. It's the most ionic compound. Trying to make this smaller, it's getting bigger. Come on, help me here. It's wrong. There we go. Trying to make it smaller so we can see this here. Okay, so what would we have here? When would we have zero difference? Can you think of an example where it'd be zero? Maybe? Similar, even more than that. Same. If the two elements in the bond, if the two atoms in the bond are the same, and you know examples of that right now. No, here we go. Diatomic ones. Well, potassium isn't diatomic. So I'm looking here at the covalent. Metals will form ionic bonds. So oxygen, fluorine, any time where the bond is between two atoms that are the same. Look at fluorine. 4.0 minus 4.0 gives you 0. That's what I'm doing here. So when the two elements in the bond are identical, then the delta, the change in the difference in electronegativity is going to be 0. This right here is your carbon-hydrogen bond. Carbon is, what is carbon? 2.5. Carbon. And hydrogen is 2.1. So what we're saying on this chart right here is from 0 to 0.4, we're gonna view that as essentially a covalent bond. From a difference of 1.9 to 3.3 is essentially an ionic bond. And so what about from 0.4 to 1.9? Well, you're getting into polar covalent territory. So let's take a look at water. Water is made up, it's H2O. It's made up of hydrogen and oxygen. So it's got two of these bonds there, but let's just ask about this one bond right here. What is the delta E of that bond? Oxygen's electronegativity is what? 3.5. And hydrogen? And the difference? 1.4. Look at that. That puts it right about here. A hydrogen-oxygen bond has a 1.4 difference in electronegativity. It is sharing the electrons, but not equally. Very unequally. The oxygen, the electrons are drawn to the oxygen more than they are drawn to the hydrogen. Meaning that the oxygen end of the bond is going to have that electron and have a negative nature to it. Not an ion, but a partial negative charge on the oxygen. And you'll see these little delta signs. It means partial negative charge, partial positive charge on the hydrogen. And so that bond is polar. That's a polar covalent bond. All right, so be familiar with this scale from 0 to 3.3, and where these aren't, in some textbooks you'll see it say, well, from 1.8 and above, it's ionic. Another textbook will say from 1.9. So this isn't a hard and fast rule. It's just saying by the time you get to about 1.9, it's starting to exhibit more ionic character than it is a covalently bound molecule. All right, so we basically have two major categories: ionic, covalent. Within covalent, we have just regular covalent and polar covalent. Still sharing electrons, but there's equal sharing, unequal sharing. All right, so now let's start figuring out how to put some names together. All right, the writing formulas of ionic compounds. So we will talk about naming and formulas in two areas. Ionic compounds are going to be named and their formulas are going to be written in a certain way. Covalent compounds are going to be named and formulas written in a certain way. There's a little, so ignore covalent for a minute and let's just get our hands around how do we name and write the formulas of ionic compounds. Cations and anions must combine to give a formula with a net charge of 0. So whether it's magnesium or sodium chloride or magnesium chloride or aluminum chloride, those bottles, those compounds of those bottles will not have a charge on them. The number of electrons that sodium loses is the number of electrons that the chlorines are going to gain. Number of electrons magnesium loses is the number of electrons the chlorine is going to gain. So on sodium, it loses 1 electron. That electron adds to the chlorine atom, you get a chloride. There's your 8 electrons, you get a chloride ion. But let's just ask the question here, what about magnesium? Magnesium loses 2 electrons. I could write 2 electrons right there, but I'm going to write my 2 electrons right there. There's 2 electrons. So what happens there? That adds to a chlorine. What happens to that electron? We got 1 electron left over. Okay, it has to add to another chlorine atom. Magnesium does not react with 1 chlorine atom. It reacts with 2. Why? Because it's giving up 2 electrons. Like I said, those 2 electrons have to have somewhere to go. This chlorine atom will not accept 2 electrons. It only wants 1 electron. You follow me? This is what's happening. So now, what do I have here? I have 1 magnesium reacting with 2 chlorines. And I'm going to get MgCl2, magnesium chloride. And I mean, I could just make this a little more complicated, but hopefully you could see what's going to happen here. Aluminum wants to lose 3 electrons. So how many chlorine atoms does aluminum have to react with? 3. You're going to get 3 of these. And these are going to all be the chloride ions. So the formula is AlCl3. Aluminum reacts in a 1:3 ratio. Okay, now, is there a simple way to figure this out? Well, this is where I gave you this. I said if you will learn these charges, I'm going to use these three examples: sodium, magnesium, and aluminum with chlorine. And we'll just do this real simply. But this is where you need to memorize these charges. What do these atoms typically form in the way of an ion? If you know that, you can then write the ionic formulas. So let's go back to what I had here. So let's just take sodium. So if I gave you these names, sodium chloride, magnesium chloride. I gave you these names. I should have written that closer. And aluminum chloride. So how you would convert this into a formula, you say, okay, sodium, what's the symbol? Na. Chloride, what's the symbol? Cl. What's the charge? This has a +1 charge. This has a -1 charge. I'm going to take these numbers and put them right there. So I have an Na1Cl1. But in formulas, we don't write ones. If it's a 1, we don't write it. So the formula for sodium chloride is just NaCl. Let's look what happens with magnesium. So magnesium, I take the Mg, I get the symbol, Mg. Chlorine, I get the symbol, Cl. This has a +2 charge. This has a -1 charge. That's what is on that list right there. I put this 2 right there. I put the 1, not the -1, just the 1 right there, and I get an Mg1Cl2, and I don't need the 1. I just simply write the formula, MgCl2. Aluminum chloride. Aluminum chloride. Charge on the aluminum, +3. Charge on the chloride, -1. Bring that 3 right there. Put this 1 right there. And we do not write ones, so I have the formula AlCl3. So if I got a bottle of aluminum chloride, I have 1 aluminum atom for every 3 chlorides. 1 aluminum ion for every 3 chloride ions. Now, is it right on this slide right here? Yeah, now it says the cations and anions must combine to give a formula with a net charge of 0. So let's just see what we're talking about here with this aluminum chloride. The aluminum chloride, it has +3 aluminum ions in it. It has -1 chloride ions in it. How many of these? There's 1 +3 ion combined with 3 -1 ions. So the total positive charge is +3, and the total negative charge is -3, and the net charge on that crystal of aluminum chloride is 0. There's a 1:3 ratio of aluminum ions to chloride ions, and it gives you a net 0. Okay, let's see if you're getting this. Try to write the formula of aluminum oxide. Aluminum oxide. Okay, what's the first thing you do? You get the symbols, right? What are the symbols? An O. What are the charges on each one of those? All right, and so what is the formula? Al2O3. That's aluminum oxide. Now let's see if that's neutral. This has got a +3, that has a -2. So 2 times +3 is +6. 3 times -2 is a -6. And see, that overall formula is got a net zero charge. It's made up of ions. There's all kinds of charges in there, but they are totally balanced out. The positive charge is perfectly balanced by the negative charge. You with me? That's what we mean by the net charge. Net overall charge, 0. Okay. This has all different kinds of examples on it, but let me point out a couple for you to work on right now. Just for a minute, we'll do 2, and then there's other kinds. Okay, well, let's see, do. Oh, you didn't get one. Do 1, 2, 3, and 5. 1, 2, 3, and 5. Number 4 gets us into a little bit different territory. 1, 2, 3, and 5. And while you're doing that, I'll get attendance. Where'd my attendance sheet go? Sarahi. Taylor. Veronica. Samantha. Maria. Carlos. Julia. Lindsay. Shayla. Blessing. Christian. Leween. Jasmine. Train. Tiffany. Jonathan. Sandra. Monica. Danielle. Matthew. Gabriel. Sam. Catherine. Brianna. Tori. Vo. Okay. What? This thing? Does anybody need this? These are on the slides, but yeah, these are very, very, very important. These slides right here. Okay, let's do these 4. Quickly here. Lithium chloride is what? Magnesium fluoride. Aluminum sulfide. All right, that's just, notice that aluminum oxide was Al2O3. Sulfur is a -2 ion, it's Al2S3. Has the same pattern there. And then what's number 5? Silver oxide. So what is that? Ag2O. Good. All right. There's those charges. There's some of the most important ions, and you should really know all of this. The nitride, the phosphide, the hydride. Now look at hydrogen. Hydrogen is usually a positive 1 ion. And you'd say, oh, that makes sense. It's right there in column 1, positive 1. On occasion, not very often, you might see something like potassium hydride, where hydrogen is actually reacted with potassium. It's reacted with a metal. Potassium wants to be +1. It's going to take hydrogen's electron rather than hydrogen losing its electron. So potassium hydride would be like that, KH. But, well, let's not worry about that right now. All right. Well, let's just do one harder one here. Let's do calcium nitride. I don't know. I might not even have it on there. Let's just do calcium nitride. So what would that be? What's the charge on calcium? And nitride? So what's that going to convert to? There's calcium nitride. All right. The next chart starts showing you how to piece the names together. So NaCl. The positive ion is sodium. The negative ion, we would look at the periodic table and see the word chlorine, but the INE is dropped and we add IDE. We call that sodium chlor. We don't call it sodium chlorine. To a chemist, this is chlorine. It's a diatomic element. So chlorine, you're talking about the element. When that element gains an electron, we talk about the chloride ion, fluoride ion, bromide, iodide. Okay, they all change the ide. Oxygen changes to oxide. Sulfur to sulfide. Bromide, oxide. So you can see those names getting together. Nothing happens to the name of the metal. Calcium, calcium. But now it's calcium oxide. Okay? Okay, now this next chart is one you have to start getting familiar with. We skipped over number 4. You see it says calcium sulfate. That is not sulfide. What is sulfate? It is a polyatomic ion. What do we mean by that? There's 1 sulfur and 4 oxygens bound together in a, think about it as a unit. It's a sulfate -2 charged ion. It's a polyatomic. Chloride is a monoatomic ion. There's just 1 chlorine atom there. It's just 1 atom. But this is not. There's 5 atoms. There's 5 atoms here, but they have a -2 charge. Not any one of them, just all 5 of them together have 2 extra electrons in there. It's a -2 charge. This is probably the best one to start with because you've heard of it, carbonate. Any carbonated beverage, any Coke, 7-Up, whatever, it's carbonated. It has some carbonate ion in it. Calcium carbonate is what's in our drinking water and makes it hard water. Carbonate, this is a polyatomic anion. I need to give you a couple examples of this so that you can start. Let me give you an easy one. Let's look at the hydroxide, an OH with a negative charge. So if I had a compound that was sodium hydroxide, all right, if I gave you that name, what you would do is write the symbol for sodium. You would write the symbol for the hydroxide. You would look at the charges on them. Where am I getting this? Got a -1 charge. It's not real clear there, but that's a -1 charge. Okay? And so this one is going to go there, this one is going to go there, and we're going to get the formula sodium hydroxide. Now let's just make it a little bit more complicated. Magnesium hydroxide. I got an Mg with a +2 charge. I got a hydroxide with a -1 charge. Okay, now pay attention. We say the 2 goes right there, the 1 goes right there, and you think, well, is this going to be the formula? No. No, because that 2 is applying only to that hydrogen right there. We want this 2 to be hydroxides. So we don't do that. We put a parenthesis around that hydroxide and put 2 outside the parentheses. So that tells us what we've got there is 1 magnesium ion and 2 hydroxide ions. All right? This here would have told me I got 1 magnesium, 1 oxygen, and 2 hydrogens. That would have been wrong. Wrong. Okay, so you need a parenthesis there. So let's look at sodium carbonate, and then we're out of time. Sodium carbonate. You've got a chart over here. Carbonate is, what is carbonate? CO3. 2 minus charge. And sodium is sodium. Okay, this one's going to be a little bit easier. We just got a 1 there, so we got a sodium carbonate. Okay. Why don't you put a circle around, these are the ones you can ignore for right now, or put a 12, 14, 21, 18 also, 14, 18, 21, and 25 and 26. I think I might have skipped one there, but the rest of those you can start playing with. And then if you want to start looking at some of these on the other side, how would you put names? I think the syllabus says the exam is next Thursday. I don't think we could do that. It's going to have to be the following Tuesday, okay? We still need 1 week to hit this. Yeah, I think so. So I'll delay that exam until the following Tuesday.